Thanks. So thanks a lot to the organizers for giving me this opportunity to speak. And I'm going to talk about morphism between periodic chains and broken Schur-Weyl duality, which is kind of a misleading title, but we'll see why. This is all based on joint work with Yvan. Okay, so here we go. I'm going to start to use this thing if it works. So I'll start with just a bit of motivation. Okay, and hopefully I'll define everything later in the talk, everything that's really necessary for us. So at the beginning, maybe we'll just do some reminders about Mod's talk and some maybe new things. This is a kind of a particular example of what we have seen in the first talk given by Mod. If we consider this space, which is D, okay, I won't use that, I think, which is just C2 to the tensor power n, okay, we can act upon it with two things. First, the Lie algebra of traceless 2 by 2 matrices, and the action is pointwise on each tensor copies. Or we can act with the symmetric group, okay, on n letters by permuting all these tensor copies. As we have seen, these action commutes, and we have this mutual centralizer properties, which gives two surjections, and each endomorphism of V, which is linear with respect to the action of SL2, can be expressed as the action of some element of the symmetric group, okay, and vice versa. This is called classical Schur-Weyl duality. There's a lot of interesting representation theoric and combinatorial applications, as we have seen, and as I won't discuss too much. So there's a quantum analog of this. We have seen it also. It was first introduced by Jimbo, and we replaced the action of SL2 with the action of the quantum group UQSL2. The action is given through the coproduct. And we replace the action of the symmetric group by some quotient of the associated Eck algebra, so by the Temperley-Lieb algebra, aTLN beta. So here, the parameter beta is the parameter delta used by mods, and I use a slightly different parameterization and send q to minus q, let's say. We still have this mutual centralizer property, okay, but here the surjections are isomorphisms. And this is interesting from a physical point of view, because we can recover the Hamiltonian of a well-known physical system, the open XXZ chains, through this TLN action, okay? So for us, okay, we'll just say that this physical model, okay, the open XXZ chains, can be viewed as instances of TLN modules, all right? So they are somewhere into the representation theory of the Temperley-Lieb algebra. We can still go one step further, because this TLN action can be extended to an action of a bigger algebra, the affine Temperley-Lieb algebra, which is infinite dimensional. And we still have some physical point of view surrounding this, because we can recover the Hamiltonian of another well-known physical system, the periodic XXZ chains now, through the aTLN action. So again, for us, periodic XXZ chains will be instances of aTLN module. So there's a problem now, because this extended action does not commute with the old UQSL2 action anymore, okay? So we can say that the Schur-Weyl duality is broken, but this is a kind of like, okay? So a natural question would be, what part of the Schur-Weyl duality still holds? And can we obtain aTLN morphism between periodic XXZ chains through this UQSL2 action? So we'll see that we'll quit a bit the Schur-Weyl setting, and I will try to find morphism relating possibly different periodic chains and not endomorphism of a given periodic chain. So we'll see a bit more about that later. For the rest of the talk, okay, I'm gonna consider first the periodic chains as aTLN modules. After that, as modules over UQSL2, or more precisely over the Lustig's extension of this algebra, which is just UQSL2 with divided powers. And at last, I'm going to give a comment about an adapted Schur-Weyl duality, so something. So let us first define aTLN. This is an infinite dimensional algebra generated by these guys. So E0 to En minus 1, omega n plus or minus 1, and there's an identity. And we have some relations which are not so important, okay? So these are the relations that I have given here for n at least 3. The only thing really important here is that this is an affine algebra. We'll view it later as an algebra of diagrams around a cylinder. So the indices are all taken here modulo n, okay? And the only really important relation for us will be this one, okay? So here, the first on the second line. And this relation says that another generating set for my algebra is given by omega n, ei, for any I fixed, and omega n minus 1. So I'll fix for a generating set omega n minus 1, and E1. We have a diagrammatical realization of this algebra as we had for TLN in Mudstock or for the Walbor algebra or all these diagrammatic algebras. And here the diagrams are planar diagrams which I draw on a cylinder. Okay, so it's again, it's kind of temporary diagrams, but I allow myself to pass through some imaginary boundary here and reappear on the other side. So I can go around the cylinder. And this is the diagrammatical realization given on my generating set E1 omega n minus 1. So what is the action of this algebra on the space C2 to the tensor power n? So I'll fix this basis for C2 to the tensor power n. So each element corresponds to a choice of n signs, x1 to xn. And I have two natural operators acting on this space. The first one is just, okay, so the explicit action is not really important again, but you can view that this one is just a linear combination of the identity, sending x1 to xn to x1 to xn, and to the permutations of the first two spins, so sending x1 to xn to x2, x1, x3 to xn. And the other operator is a weighted rotation. So I send x1 to xn to x2 to xn, x1, and I weight this rotation around my cylinder by some power of what I call the twist parameter, which is just an invertible complex number. So these two operators depend on a choice of sign, plus or minus, and a choice of twist parameter, z. And in fact, if I choose any sign and any twist parameter, I have an induced aTLN action on this space, given by E1 going to E1 plus or minus, and omega n to omega n z. And I'll denote the resulting aTLN module by x and choice of twist parameter, choice of sign. So as I said at the beginning of the talk, I can recover the XXZ Hamiltonian with this aTLN action. It is simply given as the sum of these EI plus or EI minus. And these local interactions are given through this relation of aTLN that I have underlined just before. But for us, the really remarkable thing is that the given aTLN action does commute with the action of this operator to SZ and does not change these eigenvalues. Okay, so if I consider the corresponding eigenspace decomposition of V with respect to this operator, each of the eigenspaces are in fact aTLN modules. Okay. So this guy, xn dz plus or minus, which is just the eigenspace of xn z plus or minus with eigenvalue d for 2sz, is in fact an aTLN module. And this is interesting for us because we want to study spaces of periodic chains, okay? And now we can decompose these chains as eigenspaces and look at spaces of eigenspaces, okay? So this is the first step. All right, so as I said, we want to study these spaces of periodic chains, so of different x and z plus or minus. But we have an eigenspace decomposition, and we have a natural isomorphism here given by spin flip, which links eigenspaces corresponding to one choice of sign to eigenspaces corresponding to the other choice of sign. In fact, we can restrict ourselves to the study of these spaces, okay, where we have the same sign for each eigenspace. And in fact, the only three parameters are these pairs dz, tx, which are in this indexing set. Okay. Again, the explicit form of this indexing set is not really important. The only important thing about this set is that it is partially ordered. Okay, so we have a partial ordering on delta n, which is the set indexing our eigenspaces. And we want to study these eigenspaces, or more precisely, the morphisms between them. This partial order is generated by the condition dz is less or equal than tx if t is greater or equal than d, and one of these conditions is satisfied. Okay, Again, the explicit form of this condition is not really important. But this partial ordering was known before. In fact, its restriction to the set of pairs in delta n with a non-negative first component is of capital importance in the representation theory of aTLN. This set, lambda n, which is the subset of this guy with pairs with first component non-negative, in fact, is at some technical details, up to some technical details, an indexing set for the simple modules of aTLN. Okay, so this ordering gives us an ordering for the simple modules and for the composition factors in general of like standard modules for aTLN or for some other things. Okay, it also appears in the structure of the eigenspaces. Okay, this partial order. Okay, and this structure is known. Okay, and what I mean by known is that we know all non-split short exact sequences in this guy, which is generically undecomposable, and we know it's structural diagrams, it's Schur-Weyl diagrams, and all of this appears. All of this is proven in our latest. Okay, so we know this the structure of this guy. And it is deeply related to this partial order. And this is the Schur-Weyl diagram of some of these eigenspaces. And all of the pairs here represent composition factors of a module. Okay, and all of and are in fact all the successors of this pair dz with respect to this order in the set lambda. Okay, so to summarize, the decomposition factors of this module are in fact the successor of the pair dz with respect to this order delta on delta. And as we have seen for TLN, the representation theory of the affine Temperley-Lieb algebra is especially interesting when Q is a root of unity, and this also holds for the structure of these guys. So we'll restrict to this case for the rest of the talk. Okay, and I'll only consider Q a root of unity. So for Q any complex number or a variable, you can consider the quantum group UQSL2, which is again an infinite dimensional algebra generated by some generators EF k plus or minus 1 with some relations, which are just deformations of the usual relations for SL2. And when Q is a root of unity, you typically also add divided powers, okay, so which are defined in this way with the Q factor. So there's a more formal way to do this, okay, and you need to first consider Q as a formal parameter and then specialize in some way, but we won't do that now. But we will need to know that this algebra UQSL2 with divided powers, which I denote by LUQ, is a up algebra and has a particular coproduct, which goes from LUQ to its tensor square. If I want to define a representation of LUQ on C2 to the tensor power n, I only need to do it on C2 and after that induce with the coproduct. Okay, so this is what I do. So LUQ act on C2 through this action, which is just so this representation is just a canonical deformation of the usual two-dimensional representation of SL2. So here E acts as a raising operator, F as a lowering one, and K is a diagonal operator with eigenvalue Q to the plus or minus 1. Okay, and then I can induce an action on C2 to the tensor power n through the coproduct. So for example, if I act on the chain with two spins, then F will act on this guy through its coproduct, which is this, and I'll obtain this element of the two spin chain. And in the same way, this guy will act on F will act on this guy as this. And it's not really important to follow the explicit computation, but even with the spin chain with only two signs, so for C2 to tensor square, we have a broken Schur-Weyl duality, and F does not commute with omega n. There's a little computation here that is not really important in full generality. So this Schur-Weyl duality is broken, and we don't have commuting actions now. Okay, but we can still obtain aTLN morphism on C2 to the tensor power n. Okay, through the UQSL2 action. And how do we do that? We fix two pairs in our indexing set delta n, and without loss of generality, I'll suppose that T is at least D. Okay, and then I define two C-linear maps. So I don't know yet if they are aTLN linear. Okay, they're just like maps of vector spaces. I have the map E and F, and E acts as the divided power E to the A. F acts as the divided power F to the A. And the only kind of a special thing is that I need to change the twist parameter for my spin chains. Okay, so it's kind of like a twisted UQSL2 action on the chain. Okay, so here I act on this basis element of this guy with this morphism, and I obtain this, which is just the action of E to the A on this basis element, which belongs to this space. So when are these morphisms aTLN linear? For explaining that, recall these conditions which define my partial order on delta n. Recall the domains and codomains of my morphism just defined. Then we have proven that this first morphism is aTLN linear if dz is less or equal than tx through condition A here. Okay. So if dz and tx are related to this condition. In the same way, f is aTLN linear if the succession is rather done through condition B. Okay, so this partial order also, in some sense, encodes the compatibility between the UQSL2 action and the aTLN action on the chain. This is really different from what we would have obtained from a Schur-Weyl duality setting, as we relate two different spin chains and we can change the twist parameters in our morphisms. So here, the twist parameter z is a priori different from the one x that would be obtained here. And so we don't obtain endomorphism of a given aTLN module, but rather like morphism relating different aTLN modules a priori. Okay, so this is pretty different. There's a natural question. Do I have now all the morphisms between these eigenspaces? So do these morphisms here, given in this theorem, generate all this space? Okay. So the answer comes from an analysis of the structure of the XXZ eigenspaces and is yes, except when some condition star is met. So I'll define condition star now. But to be precise, it is yes, except in a finite number of cases. So condition star is given here. It's pretty technical, so don't bother too much with it. But it says that the codomain here must have a non-positive D, which satisfies this relation. And the domain is entirely specified by the codomain and must have no successor through condition A. So there must be no other pair satisfying this if I take for the pair Tx. Okay, so the only thing that you need to know is that this happens only for a finite number of pairs dz in my infinite indexing set delta n. Okay, so this is really the answer is really generically yes. Right? And I just want to emphasize also that our structural analysis done here also give the image and kernels of all morphism between XXZ eigenspaces. So I have a structure, the structural diagrams of all image and morphism between these eigenspaces, and I have all the corresponding non-split short exact sequences. So what happens when condition star is met? To generate all the space, we need to consider one additional morphism. And what is it? Okay. In this case, the head of the domain, okay, so the head of this guy is isomorphic to the so-called of this guy. So we have a natural projection and a natural injection, which gives a natural aTLN morphism. The problem is that we have not yet succeeded to realize this map through the LUQ action in full generality, okay? But this should be done. And, but we still have a concrete realization of it, which is given through a morphism defined by Saint-Aubin and Morin-Chen Saint-Aubin, which relates our eigenspaces to the standard modules of aTLN that were introduced by Graham and Lehrer and that are similar to the ones defined by mods for aTLN. So to finish, okay, in short, morphism between XXZ eigenspaces, okay, generally come from the action of UQSL2, okay. So there's a part of Schur-Weyl duality that still prevails, and this is some kind of a stretch because we consider like morphism between different periodic chains. But what we have seen is that in general, okay, there's no non-trivial endomorphism with respect to the aTLN action for a given periodic chain. So if you want to maximize this number of aTLN endomorphism, our study suggests to replace the study of these periodic chains where this direct sum of eigenspaces is done for a fixed twist parameter, to replace the study of these guys with that of these modules, where I allow myself to change this twist parameter at each sum end of the direct sum, and I'll change it in a compatible fashion with the partial order on delta n. Okay, so this is what our study suggests, and in this way we would maximize, as I said, the number of aTLN endomorphism, and the endomorphism rings should at least generically generate interesting subalgebras of LUQ, okay, which will depend on the parameter dz appearing in this decomposition. Okay, cool. So thank you. This is all.
Plenty of time for questions and remarks, comments.
Your last sentence suggests that even if you consider M, then the quantum group will not be the centralizer, right? Because you're writing it's interesting. So you still have elements of the quantum groups which do not commute with your chain.
Absolutely.
Okay. And there is no way to unbreak the Schur-Weyl duality then.
Not with this action on C2 to the tensor power n.
Okay, say then you take this interesting subalgebra. Do you have any idea of what will be the quotient corresponding to the centralizer?
No, not yet. But not yet. This is really this is pretty ongoing work. This last theorem was found just like a month ago. But yeah, I plan to study these quotients too.
Okay.
Like the explicit form of like the explicit subalgebras appearing here are not yet like known to me.
And I think the other question is it so this interesting subalgebra? Do they do you recover the whole centralizer from them, or there will be something more commuting with your Temperley-Lieb action?
In general, at least generically, this should be all the central.
The representation it looks like the representation for the blob algebra.
Yes, you're right.
Do you get other kinds of representation though, the kinds of things that don't look like blob things?
Okay,
if that makes sense.
Yeah, it's a really good question. Okay, so the structure of the blob, the blob algebra is, again, at least generically, isomorphic to a quotient of the affine Temperley-Lieb algebra. Okay, so you have a lot of modules that go through this quotient. Okay, and these eigenspaces, okay, go through this quotient. Okay, and in this case, okay, this is not in fact a good diagram. So this is the diagram of the corresponding to the structure of the standard modules for aTLN. Okay, so this is the structure of standard modules for aTLN. And when you pass to the quotient, you get standard modules for blob. Okay, and this is the structure that you would obtain. Okay, but for the XXZ eigenspaces, I'm sorry, this wasn't not true what I said. You need to switch some arrows here. Okay, so it's the same composition factors, but if you want, the non-split short exact sequences are kind of modified. Okay, all right. And in this case, I don't think it was known that the corresponding Loewy diagram was part of the representation theory of the blob algebra. But showing that it is part of the representation theory of aTLN and that it passes through this quotient to the blob algebra shows that it is at least generically inside this representation theory. These are all the standard modules have this form here. But sometimes this diagram can be simplified and there are like some coincidence of pairs. So it can become a line if you want. Yeah, and it is always finite. Okay, at some point, these first components are larger than n and you need to truncate. So I did not try. It took us a long time to find this structure, just the structure. So you were really just beginning the work on this. Yeah, it should be. Yeah, but yeah, I don't.
Speaking of a quotient to the blob algebra, is the quotient by some central elements?
Yeah, that's right.
Okay.
Which is called the OOP operator, I think.
Okay, so you can also define spin chain for the blob algebra. So does your result, do you think that from your result you could conclude that in the blob algebra, the standard will have the same structure with all arrows pointing in the same direction. And when in the spin chain, you all have the alternating.
Yeah.
Okay.
Yeah, because all of these, it depends how you define. I would define like the blob action on the spin chains through this quotient. So it's kind of like tautological. But yeah, that I think this is the natural thing to do. Really, we kind of lose a priori the physical motivation for the study of these things. It is just like wanting to maximize these endomorphism rings, the dimension of these guys.
Unless there's a pressing question, I think we should thank Théo again.